I'm going to quickly move into introducing our first presenter this morning, which is Dr. Sarah Lancaster, who's an assistant professor with Kansas State University. And I see that she put her camera on, so we're getting there. Sarah was raised on an integrated crop and livestock farm in East Central Missouri, which is in the United States, and I think Missouri, but I don't know. She holds degrees from the University of Missouri, North Carolina State University, and Texas A&M University. She's been an assistant professor at Kansas State University Agronomy Department since November 2019. She's at the North Central Weed Science Society meetings right now, so she's busy, and I'm happy to have her fit in with us today. Her efforts are focused on weed management, extension and research. Her and her husband also have two children, Levi and Caleb. And so welcome, Dr. Sarah Lancaster, talking about herbicide and soil interactions.
Thank you for that introduction, Tammy. I am here at the North Central Weed Science meetings in lovely Grand Rapids, Michigan. But I have to tell you, my heart today is kind of with my home state of Kansas. They had some pretty crazy last night. So if you're a praying type, I said, we're going to talk herbicide and soil interactions today. So I hope that internet connection works well and everything is great. We've tested this a couple times, and I think it's going to be a good morning. So residual herbicides, just to make sure we're all starting from the same foundation here. So residual herbicides, we put them down at planting, right? The goal, sometimes I tell my farmers in Kansas, the best time to kill your weeds is before you ever see them. So use residual herbicides, right? The goal is generally to apply them at planting to prevent emergence of weeds and preserve crop yields. We also, as we have moved into this kind of mindset of zero tolerance thresholds for herbicide resistant weeds, have started increasing the use of these products as early post-emergent applications. So trying to lengthen the time of that residual activity to ensure that we have good weed control through the time of crop canopy. So those are the types of products we're going to be talking about today. So one of the things that makes residual herbicides effective is their ability to persist in the environment. Okay, so when I'm talking about herbicide persistence, we're just talking about the length of time that that herbicide is active. And I stuck a picture of a really gnarly pepper plant up here on this slide to remind me to tell you guys that today we're going to focus primarily on how these herbicides behave in the soil. But some of these products, particularly pyridines, things like group 4 herbicides like clopyralid, I think you guys use quite a bit in your cropping rotations. And actually, I had a conversation yesterday about a sister product called aminopyralid that's causing problems in the Dakotas here in the States. And so, those products have the ability to persist even in plant residues or even in livestock manure, right? So if you read the labels for these products, it talks about not transporting hay that has been sprayed with these products. It talks about withdrawal periods for livestock so that they're not grazing forage or hay that had been treated prior to moving them off the property, because these products can persist a long time in the environment and cause injury to sensitive plants. So, this ugly pepper plant that we're looking at here, it may have been, this injury may have been the result of, potentially using straw for bedding or using lawn clippings in your compost that then caused that crop injury as the product was released from that plant material. So persistence is a very complex topic, and we're going to skim the surface here in the next 45 minutes or so. So when we talk about herbicide persistence, we generally describe persistence in terms of half-life, okay? And so to determine half-life, you can do a couple of things. You can either apply it to the soil in the field and go collect samples and measure the concentration of herbicide in that soil, or oftentimes we'll do laboratory experiments in a more controlled environment. So I'll show you some half-life numbers and talk about some half-life numbers later today. And so that's how those numbers were derived. Okay, typically we're talking about half-lives in the order of days. For herbicides that are intended to be like soil sterilants, you're going to talk about, months of activity there. And of course, that persistence is influenced by the rate of the product that you're going to use. Okay. So as companies are developing these products to be used as residual herbicides, what they're really looking for is kind of a sweet spot there. They want the herbicide to stay in the environment long enough to provide that extended weed control that we need. But the kicker is that herbicide also has to dissipate or break down or leave the environment fast enough that we don't have carryover, herbicide carryover. So carryover is just the term that we use when we talk about harmful amounts of a herbicide remaining present in the soil to the extent that it negatively affects the subsequent crop. So I spray product X on my soybeans in 2021, and I come back and I plant field corn in 2022, and I see some evidence of crop injury as a result of that herbicide that I applied last year. So that's herbicide carryover. So here are some examples of herbicides that are prone to carryover. This is by no means a comprehensive list, but just to give you an idea of some of the types of products and what some of those typical half-lives in the field look like. And then also, we're going to spend a good bit of time today talking about how these products break down. So just to kind of warm you up for that conversation, we have some examples of how these products are broken down. So, talking with Tammy as I was prepping, she specifically kind of asked about flucarbazone and clopyralid. So group 2 products some of them are pretty notorious for carryover issues, especially as we move into extreme pHs. And clopyralid is one that in a lot of regions, we're having some concerns about that going into 22 because of dry weather. Okay, so looking at the half-lives, you can see here half-lives range from anywhere from 8 to 23 days for clopyralid, all the way up to potentially 300 days for products like sulfentrazone. And so the other thing we need to say here as we talk about carryover is that it's an interaction not only of how long that product sticks around, but also how sensitive the next crop is and how efficacious that product is, that what's the effective dose of that product on a particular crop. So just keep that in mind, that it's not going to be the same for all crops, which you guys are sharp agronomists. You probably already had that down. But as we look at some of these mechanisms of degradation, one of the things to point out is that the most common form of degradation here is microbial degradation. So we're going to spend some time really looking into the factors that affect that. But other things that can cause pesticides or herbicides in specific to break down would be things like chemical reactions like hydrolysis, which tend to be more active at lower pHs oftentimes. Some products are even susceptible to photodegradation. So if they sit on top of the surface of the soil, they take in energy from the sun, and that actually causes the bonds within that molecule to break down, and then that herbicide will degrade. So we're going to jump into that a little bit more here in a moment. But let's think about, before we talk about degradation in specific, I'd like to spend just a few minutes thinking about what happens to these herbicides after we apply them, right? Here in the States, we've spent a lot of energy talking about off-target movement of herbicides, especially with regards to some of our group 4 products like dicamba and 2,4-D. So that off-target movement is potentially one thing that happens to herbicides. But let's look at what happens to these herbicides once they hit the soil, okay? So the first thing that I want to talk about here is this plant uptake, right? When we're talking about herbicides, this is what we want. We want the weeds to take these herbicides in and to be controlled. So as we look at this particular slide here, we're looking at, again, some examples of herbicides and then how they're taken up, okay? So very often these products are going to be taken up through the roots of the plants, sometimes through that emerging shoot tissue Some of these products will have both pre-emergence and post-emergence activity, so they can be taken up through shoot tissue that is exposed above ground. But today we're going to focus on these processes of taking the herbicides in through the roots, okay? So the number one thing that has to happen in order for that to occur is that herbicide has to be dissolved in the soil solution. So it has to be present in the water that's in the soil, okay? So the opposite of being available in the soil solution would be this idea of sorption, okay? Sorption. And sorption is just, it's kind of a cheater word, because there are a lot of things we don't understand about exactly how herbicides are sorbed. Sometimes we're talking about things that are adsorbed, and sometimes we're talking about things that are absorbed. Typically in the soil, we assume that we're talking about a process called adsorption, which just means that herbicide molecule is sort of temporarily taped or temporarily stuck onto the surface of a soil particle or soil colloid, okay? And so the cool thing about that is that very often that means that herbicide can sometimes be attached and then it can go into the soil solution. And so there are equilibria at play here that the herbicide is going to try to settle out at. This slide I just included to show some examples of some of the chemistry that really goes on in the soil when we're talking about sorption. So one of the more sort of permanent things that happens is this idea of ligand binding. Okay, and so there's an interaction between, for example, these hydroxyl groups here on this this glyphosate molecule that I drew in here, interacting with the metals, the chemical metals here, the iron, on the surface of the soil colloid. Okay, so that's one example. A less permanent example would be these electrostatic interactions. So we've got basically cation exchange going on here, right? So this is a paraquat molecule here. That the net negative charge of this molecule, the net positive charge of this molecule is going to interact with the net negative charge of that soil colloid. So electrostatic interactions based on the chemical charge of the herbicide and the chemical charge of the soil colloids, right? So when we talk about cation exchange capacity, right, this is an example of a cation right here. And then excuse me, the last thing we need to look at here are hydrophobic interactions. So these are primarily interactions with soil organic matter. So when you read your herbicide labels and you see that high organic matter soils require higher rates of herbicide, this is why, okay? Because some herbicides are hydrophobic. That means they don't like water. They like things with lots of big, long carbon chains, okay? Soil organic matter has lots of big, long carbon groups. Okay, so those herbicides that are hydrophobic are attracted to things like soil organic matter. Now, I went through these three different types of interactions, and I will tell you that they are three distinct things, but oftentimes there are combinations of these types of interactions that are occurring all at the same time, but with some molecules, okay? So we've talked about plant uptake, we've talked about sorption. Now let's talk about leaching, okay? So the other thing that can happen if the herbicide is not adsorbed to the surface of the soil is that it can leach, okay? And leaching is just the process of that herbicide moving down through the soil profile and then out of the soil profile. Okay, so here are some data that were developed by a scientist that works for our Department of Agriculture. He spent much of his career in the state of Colorado. Okay, so they were looking at sulfentrazone leaching. Okay, so they conducted this study in 2008 and 2010. And what I want you to notice is The differences in those graphs. So on the y-axis, we've got the depth at which the samples were taken. Okay, on the x-axis, they've got the sulfentrazone concentration. Okay, so shallow soil is up here in this top set of bars. Okay, so notice the differences in 2008 and 2010. Sulfentrazone is a herbicide that is really not very tightly sorbed to the surface of the soil. So look at my notes over here. In 2008, they irrigated the site immediately after application. So take a look at how much of that sulfentrazone is remaining and what would be, the area where we want that herbicide in order to control weeds, right? That top 7.5 centimeters of soil. Okay, so there really wasn't much left when they had that rainfall right away after application. But now when we wait a week and a half to get precipitation after that herbicide application, look at how much more of that sulfentrazone was still present in that upper 7.5 centimeters of soil, even up to a week after the herbicide application. Okay, so then they got 71 millimeters of rain, and essentially that herbicide, the sulfentrazone, was very low levels of detection throughout the soil profile after that rainfall occurred. So one of the comments that I want to make here at this point is related to picking pre-emergent herbicide programs. It's important that when folks are thinking about their pre-emergent herbicide program, that we're looking at herbicides that have a variety of solubilities, because something like sulfentrazone is not going to stick around very long after it rains. It is going to be activated and available to the weeds with very low levels of precipitation. If you think about something like the group 15 herbicides like metolachlors, acetochlors, those products tend to require a little bit more rainfall. They're a little less water soluble. They're going to stick around a little longer, but they do require that activating rainfall. So, building pre-emergence herbicide programs, you need to look at, not only your weed spectrum, but also thinking about how am I going to get those multiple effective modes of action that are going to give me both short-term control if I don't get an activating rainfall, but also longer-term control to last a little bit longer if I do get a rainfall. Okay, so we've talked about uptake, we've talked about sorption, we've talked about leaching. Now let's talk about degradation. This is where we're going to kind of camp for a while and spend pretty much the rest of the time this morning. So there are a few things that can happen to herbicides in terms of degradation. One, I mentioned briefly earlier, photodegradation, and these are just chemical reactions caused by light. So certain types of bonds within the herbicide molecule can absorb light, and when that happens, that extra energy causes that molecule to break apart. So Tammy told you guys I have 2 kids. My boys are way into building things with Legos, right? So 9-year-old Levi builds a fantastic structure or gadget. His 6-year-old brother comes in the room with all of his energy, right? Puts all of his energy into that creation and breaks all those bonds between those bricks. That's the same thing that is happening with the energy from the sun and those herbicide molecules, just on a much smaller, more abstract scale. Okay. So photodegradation is one thing. Chemical degradation is also a process that happens. It is more common or more impactful, more important than photodegradation, but much less important than microbial degradation. Okay, so chemical degradation by definition is just the result of reactions that are not directly the result of living organisms. It could be argued that all of the microbial degradation is also chemical degradation because much of that happens as a result of enzymes that are released into the environment. But in this case, we're talking about specifically interactions that don't involve living organisms. And one thing that's important to note is that soil pH is a very important influence in these reactions. Specifically, hydrolysis is a pretty common type of reaction that involves basically water trying to steal a proton from that herbicide molecule. Okay, so at lower pHs, that is easier, and that happens more easily. Okay, atrazine is pretty much the poster kid for this idea of pH mediated hydrolysis. Okay, so here's our atrazine. The probably the most common primary degradative atrazine is this diethyl or desethyl atrazine here that you can see it requires microbes in order to be produced. On the other hand, if you're in a low pH environment, you can have hydrolysis, okay? And so you get a totally different byproduct or different metabolite here when that happens, because instead of just taking off one of the carbon chains, like you do over here with the dealkylation reactions, what you're doing in hydrolysis is you're pulling off the chlorine that was stuck at the top here. Okay, that's where that chemical attack happens, is there at that chlorine molecule. Okay, so you get a different product. And this is why when we look at environmental fate studies, oftentimes they're looking at not only the parent molecule for atrazine, but they're looking at all three of these metabolites in order to determine what is going on with the product there. Okay, so we've talked, excuse me. We've talked about photodegradation and chemical degradation, and now microbial degradation. And so this is just herbicide breakdown. It's caused by things that are living in the soil. The main players here are going to be bacteria, but also actinomycetes, fungi, and algae to some extent. Okay, so some things that influence the rate of microbial degradation. Number one would be sorption, right? If that molecule is if the portion of that molecule that the microorganisms are going to attack or target to start breaking down is bound to that soil colloid, it's not available to the microorganisms. Okay, so if herbicides are tightly sorbed to the soil, they're not available for microbial degradation, and they're going to stick around. They're going to have longer persistence. Okay, something else that can impact the rate of microbial degradation is this idea of previous applications. Okay, so here's a sulfonylurea herbicide. This work was done actually in Israel on some pretty sandy soils. Okay, but what they did is they looked at sulfosulfuron applications on soils that had previously had no applications, and then 1, 2, 3, 4, 5, and 6 prior applications. Okay, so they pre-treated the soil, and then they came back and they sprayed the sulfosulfuron, and then they went in and they measured the concentration of the herbicide. Okay, and the key takeaway from this graph is you look here over time on the x-axis, and then the herbicide concentration here on the y. What you're seeing is that herbicides that had no prior exposure, so the solid line here, the open circles in the solid line, no prior exposure to sulfosulfuron, those soils, the herbicides stuck around longer in those soils. Okay, so the flip side would be to say that the herbicide was degraded more rapidly in soils that had previously been treated with the herbicide. This is a phenomenon we call enhanced degradation, and it's not unique to sulfosulfuron. So microbial breakdown, as I mentioned previously, is mediated primarily by enzymes, right? And so if you think about the bacterial cells as little factories, they have to kind of get geared up to make these enzymes. And the community, well, I should say this differently, rather than the cells, the community, the microbial community has to get geared up to make these enzymes, okay? Bacteria have very short life cycles. They're turning over very quickly. If you put something in the environment that a particular bacterium or type of bacterium is better adapted to use as an energy source, that particular bacterium, that population is going to grow. You're going to have more of the enzymes needed present because you've had that prior exposure. Okay. So microbial degradation can be sped up or enhanced by previous applications of the herbicide. All right. The last thing we're going to talk about is environment. Okay. I kind of led off with some preliminary comments about dust storms in Kansas. Some of that is obviously related to the frontal system that moved through much of the central U.S. Yesterday, but it also has to do with the drought situation. Okay. Significant portions of Western North America have been very dry. And this has a big impact on herbicide carryover. Okay. So we're going to look at some of the reasons why that occurs now. Okay. So the number one reason is that these soil microorganisms, most of them are kind of picky about the environments that they want to be in which they want to be active. Okay. They need to have the right temperature and they need to have the right soil moisture content. Okay. When the soil dries down, microbial activity basically slows down with it. Okay. Then what happens when moisture is returned to the soil, we see a big spike in microbial activity when they all wake up and they're kind of starting the race. They're like the rookie runners in the 5K, right? They're gonna start out running just as hard as they can, and then they level off. Okay, so that's what happens when we re-wet soils, just in general. Okay, and a lot of times that big spike in CO2 may or may not be associated. Let me say that differently. That big spike in activity may or may not be related to increases in degradation. Okay, so soil moisture effects on herbicide degradation, though. This is some data that came out of a 2002 paper looking at isoxafludol degradation. So I know that isoxafludol was not on the list of products that Tammy and I talked about prior to putting these slides together, but these are really the best research data that I've found to illustrate what happens in dry versus moist soil. Okay, so if we look here, so we've got this solid line here is our isoxafludol, our parent compound here. So we're going to watch that go down. Okay, so here in the dry soil, we can see it started at 100% and then went down at 56 days. There was very little left. Okay, if we move into a soil with a lower water potential, we have starting at 60%. Okay, and it went down. It leveled off around 20% of the available. Okay, or what was applied. And same thing here. We started at 60%, and in this case, we were for our parent compound back down again closer to 0. Okay, so we have to have soil moisture in order for the bacteria to function properly. You have to have soil moisture. And so that's why in years like 2022, when we're coming out of a very dry winter, we have some concerns about herbicide carryover. The other big driver of soil microbial activity is temperature. Okay, bacteria really like to hang out in temperatures that are somewhere around room temperature. Okay, so that 25, 27, maybe 30 degrees Celsius. Again, there is some variation among the different types of bacteria. Okay, some of them like it cold, some of them like it hot, but in general, we're looking at that 25 to 30 degrees Celsius is kind of the sweet spot for in terms of soil temperature for maximum microbial activity. Okay, so here we're looking at another sulfonylurea herbicide at 2 different temperatures. Okay, so the sterilized soil has no microorganisms in it. So you can see that breakdown of this product is primarily driven by microbial activity. Okay, so we have cooler temperatures here. So how much is remaining? Okay, when we get out to all the way out here to, okay, well, let's take a minute back. This graph on the right stops at 75 days. So let's come over here at 75 days. On the colder graph, we're still at 20 or so % of the applied herbicide remaining in the soil. Okay, colder temperatures, we have about 20% remaining at 60 or 70 days. We come over here to warmer temperatures, and again, 16. Remember what I said was the ideal. I said the ideal was 25 to 30. So we're not even at the ideal temperatures here. But at 16 degrees Celsius, when we get out to 75 days, they're essentially zero in terms of the amount of product that's remaining. So I put this here to illustrate that warmer soils result in more rapid soil degradation. The caveat to that is you have to have the soil moisture in order for that to work. So let's look now at the effects of pH on soil carryover of herbicides. So these are some data for imazethapyr that were put together actually at Michigan State, ironically enough, given my current location. So they're looking at imazethapyr persistence at a pH of 5 and a pH of 7. Okay, so the parent compound is represented by the black square. So that's the top line here. So imazethapyr, we're looking at, it really never dropped below 80% of the amount that they applied. Okay, even after, so they're talking weeks. So we're going out almost a year here. Okay, if we come over here to the pH of 7, so a neutral pH, look at how rapidly that product breaks down. So by the time they get out to their endpoint here, 40 weeks after application, they're down somewhere around probably about 30% of the herbicide that they applied is what's left in the soil. Okay, so we talked about how atrazine is going to break down more quickly at a low pH. Here we're looking at a herbicide that's going to break down more slowly at a low soil pH. Okay, so there are interactions with soil properties and the herbicide that you applied that will determine the potential for carryover. One of the things that Tammy brought up when we were kind of prepping for this was to talk about the effects of tillage on carryover. And that's an interesting thing to me because I get this question a lot, right? So you can till your soil and sort of, the thought would be that you're going to dilute the herbicide that you have in the soil. But what are you actually doing to the concentrations of herbicide? And so these are some data. They were looking at applications of clomazone. Okay, so again, they have 2 years, and they were looking at conventionally tilled systems, reduced tillage systems, and then they had pre-plant incorporated. So they were doing some light tillage to incorporate the clomazone, or no tillage to incorporate the clomazone. And of course, clomazone is a herbicide that has that's very, very prone to volatility. Okay, it has a very low vapor pressure. Doesn't take much for that herbicide to go from a liquid to a gas and escape in the environment that way. Okay, so we're looking here at 1987. What I want to do is look at the conventional till, the square, the solid square versus the solid circle. Okay, so in 1987, the solid square, our conventional tillage system with incorporation. So you're looking at shoot fresh weight here, okay, of wheat as an indicator plant. So more wheat biomass means there was less herbicide in the soil, okay? So here we have less herbicide in the soil with the PPI versus with just the straight application, okay? I want my mouse to come back so I can point to that for you guys, okay? So less shoot fresh weight, more herbicide in the soil with just a pre-application no tillage. That was the year of 1987. Now, the year of 1988, take a look at these results. It's the exact opposite, okay? It's the exact opposite. And here's what I want to do. We're going to come over here and look at their rainfall data. And look here at their departure from average rainfall. 1998 and into 1999, which would be the time period when these data were collected, they were much below average in terms of their precipitation. Okay. And so the point I want to make here is not so much to try to parse out how does tillage affect carryover. I want to just reemphasize the fact that the key driver that's impacting carryover potential here is that precipitation. Okay. Precipitation is what's going to be the key driver there. So let's wrap up with a few thoughts on how to prevent carryover. Okay. Number one is reading the labels. I spend a lot of time reminding folks that the label is the law. And even though that label is not very fun to read, it is where you're going to find the information about what is the correct rate for your soil and your environmental conditions. Living in a state like Kansas, where we have, much like you guys, we have a lot of variability from east to west in terms of precipitation gradients and different soil pH situations. And so, reading that label and recognizing where you're planning to use this product is step number one. Step number two is to respect rotation intervals. Those rotation intervals are developed with an abundance of caution on the part of the registrant. So respect those rotation intervals, and that should keep you in the clear for the most part. A third factor to think about is just to be aware of varietal differences in sensitivity. I think you guys are going to hear some talks about maybe field peas and other types of legumes later today or later this afternoon. Some of the crops that have less that have just had less breeding activity. Okay, there's still quite a bit of varietal sensitivity in terms of response to herbicides. Okay, so things like corn and soybeans, that gene pool unfortunately seems to be not maybe as broad as some of the other crops. And so just being aware of the differences in varieties in terms of the herbicides you're using, especially with things like the ALS inhibiting products or maybe sulfentrazone or metronidazole. And then the last thing I want to talk about is just the importance of conducting a bioassay and the process of conducting a bioassay. In situations where you've got particularly dry conditions, maybe you're kind of right on that rotation interval that is recommended or required by the label, but it's been really dry and you're just not sure. There are a couple of things you can do to conduct a bioassay. One would be to go out and just plant a test strip in your field. That might be one thing to do. Something else you can do if you're trying to be a little more proactive and plan a little further ahead and have a little more controlled environment would be to go and actually collect a soil sample. So collect representative soil samples from your field. You're looking, again, for that zone, that root zone where you're going to plant your seed, that seed bed. Okay, so you're only going 5 or 10 centimeters here. So you're going to also then try to find, in addition to the field where you want to plant, you're going to try to find a similar field that wasn't treated. Okay, so then you're going to take that soil, keep those two samples separate, your field in question, your non-treated field, and then you're just going to grow a little garden in a pot. Okay, so mix that soil, plant the seeds, put it in a window, keep it moist, and then you should have an answer within about 2 to 3 weeks. So, hopefully your crop seeds are going to come up and you're going to be able to look and see if they have emerged and are growing normally, or if they have injury symptoms that are consistent with the herbicide of concern. Okay. And so this is going to require knowing a little bit about herbicide symptomology, herbicide mode of action in order to distinguish that. And there are a ton of good references and resources out there to do just that. All right. I am checking in on my watch here to make sure we're still good on time. And that was the slides that I had prepared. Okay. Please feel free to reach out if you would like. My email address is listed here on the screen. My social media accounts are listed there as well. And also I'll put in a plug for my podcast. I don't have the logo for my podcast up there, but it's called The War Against Weeds. We focus primarily on the north central region of the United States, but we do branch out, and the feedback we're getting is that it's a good for just learning and remembering some of those kind of basic weed science principles that are important for management topics that are pretty timely. So with that, Tammy, I will look to you for questions. I see a couple have popped up in the Q&A.
For sure. So we do have a couple. One is going back to sulfentrazone, and which we would know more commonly as a Group 14 authority, and just wondering what the soil type was like in that Colorado study, if you know that, and what that would be like in comparison to maybe what we might have here in Manitoba, of course, or Western.
Yeah, that's a great question, and I should have double checked my memory on that. I want to say it was sandy loams, but I need to go back and double check that. I will do that.
More prone to leaching than probably our clay can contain.
Yeah, more prone to leaching. Yep.
Okay.
Yep.
The other question here, and I'm going to use a term that John Hurd uses quite frequently. So poised soils. So when we're talking about microbial degradation, when we've got those microbes sort of poised to degrade in subsequent years, just curious if there are other herbicide groups that are more prone to having that happen, or if it's compound specific, like active ingredient specific, or how that exactly shakes out.
So the poster kid for enhanced degradation, in my opinion, is atrazine. Right, like that's the one we kind of go to the most. I would submit to you that it probably anything that is microbially degraded has the potential for that to happen. There's not a ton of work in this area anymore in terms of environmental fate, and so there just aren't a lot of good examples out there to put good quantifiable numbers to that. But yeah, I would submit to you that anything that's microbially degraded has the potential for that.
It's not as sexy probably as herbicide resistance to study environmental fate, I suppose. That might be it.
Well, and so here's the thing. In the 80s and 90s, they had all these new products coming out, right? And they had to figure out what was happening to them. We haven't had a lot of new products lately. So, but I think as we see more interest in increased interest, continued interest in sustainability and environmentally aware consumers, I think we're going to start to see more of this coming back a little bit. So I'm kind of excited about that.
Right. I'm going to throw one in before I get to Lindsay's question, and that's going to be with the clomazone study. I'm assuming that was done with the older type of formulation, not the micro-encapsulated formulation. Any speculation on what it would do in an ME compared to what it did there? I'm throwing you under the bus here. I'm sorry.
No, that's a good question. Make me think here. So, the encapsulation is designed to help with that, right? And so I think I don't know that you would see shifts in the patterns, Tammy. You might see shifts in the values, if that makes sense.
Absolutely. I think the point I was trying to make in my question is that formulation does matter, right? That it does have some impact on all of that as well. So now to roll over to Lindsay's question, which is soil organic matter. My understanding is that it's similar to, say, having clay content as far as that whole cheater word of sorption. But, and I'm going to steal cheater word. I'm going to be using that all the time now, as I use this cheater word. But anyway, what's the impact of soil organic matter levels? Where are we at there?
Soil organic matter absolutely matters. In some ways, it's probably, I don't want to say it's more important than clay or less important than clay. It's different than clays. But it absolutely matters in terms of sorption. There is less evidence about how it directly affects degradation, right? If you go kind of theoretical, the more organic matter you have, the more likely you are to have the microorganisms that are alive that break down the herbicides. But that link is not, that degradation link is not as strong as the sorption link.
Right. And Lindsay has added a qualifier in here that Penn State seems to say differently than the Canola Council of Canada about high meaning something different in different locations. And I don't know what Penn State is saying, so I'm blissfully ignorant of that. Sorry.
I mean something different and different. So I don't know if it's just the fact that you can't just say high organic matter. Like if you look at a lot of the labels, you know, they talk about the cutoff a lot of times like 3%, like there's a 1 to 3% and then a 3 to 5%. So maybe that, I don't know.
And then just a final one as we are at our time. Is there a soil temperature that is too high for microbe activity? And I understand that there is, but I'll let you answer it because.
There is a too high, but that plateau is not as obvious as when you go cold, right? Like the response when you get cold is much faster and much more drastic than when you get too high.
And that soil temperature for too high of microbe activity is also too high for most plants to have a happy life as well. So
yeah, and I think interestingly, you do see like diurnal variations in microbial activity, and they do go down a little bit in the summer when it gets really hot.
So. I think they're sipping pina coladas on the beach at that point. That's just my own personal
not a bad plan.
Mm-hmm. Perfect. All right, let's wrap it up there. Thank you so much and great questions. So really appreciate you taking time away from your meeting, and there's a round of applause here in the room as we do with everyone. So thank you so much, Sarah. Okay.
Thanks, Tammy.
Have a great day.